Hey, everybody, and welcome to Yosemite National Park at Horsetail Falls. Around the vernal equinox, every year it lights up like it's on fire. This is due to some really interesting science involving light. And we're going to be learning a lot about waves, light, and sound in this video. Well, first off, light and sound travel as waves, but what is a wave? Well, a wave is merely a transfer of energy. And this is without the transfer of matter or stuff. The matter doesn't move along the wave. And all waves have speed, frequency, a wavelength, and an amplitude. Let's look at what those are. So we have two types of waves. We have longitudinal and transverse waves. Longitudinal waves go back and forth. Transverse go up and down, up and down. Types of longitudinal waves are also called compression waves, and these are associated with sound and earthquakes. So those go back and forth, whereas more often light is seen as a transverse wave going up and down, up and down. Here are two diagrams of those where we have the parts, and we're going to start looking at that thing I mentioned, a wavelength, right? So we have compressions in longitudinal waves. They're also called compression waves for a reason, right? They have compressions but rarefactions where they're far apart. We can also see that we have the transverse wave going up and down, like we think of as a traditional wave. It has a trough at the low point, crest at the high point. And the distance between two crests or two corresponding parts of the wave is the wavelength, and the amplitude is how much energy that wave has. It's seen as brightness or loudness, and that is how far up and down it goes. And this diagram you should have drawn in your notes and imprinted in your brain. Some properties of light are that light travels really fast, 299,000 meters per second, 186,000 miles per hour. This is a lot faster than sound. Okay? So just get that right out there. Light travels a lot faster than sound. And light can travel through the vacuum of space, whereas sound cannot. Light does not need a medium or stuff to travel through. Sound, because it's a compression wave, needs stuff to compress. Light, not so much. Light also, unlike sound, exists as both a particle, a photon, and as a wave, called the wave-particle duality. This is a rainbow. How does a rainbow actually happen, though? Right? And how do other things like that fire waterfall we saw at the beginning, how's that work? Well, we have all types of light in the electromagnetic spectrum. Light encompasses this entire spectrum or arrangement of frequencies and wavelengths. You do not need to write this down, by the way. Just kind of take it in for what it is. Different parts have different uses. You have longer wavelengths towards that red end, shorter wavelengths towards the purple end or violet end. And when that white light goes in, it has all the colors of the spectrum. Well, it refracts off of water, in this case a raindrop, and that separates all those wavelengths or frequencies of light. And so we see that as all the different wavelengths of color. Now, this partly becomes the nature of waves. They can do three things when they strike an object. They can either be reflected, this is like in a mirror, or an echo if it's sound. They can be absorbed and just go straight into it. Remember, the darker objects will absorb more thermal energy, right? And be warmer than lighter objects, or they can be transmitted straight through it and go through from one side to the other. And this is in a way is how we see color. We would see this as red because all the other wavelengths of light are absorbed, but the red one is reflected back up into our eye. And so we end up with reflection, right? How we see colors and things actually being reflected, and refraction. This is a form of transmission, whereas it's the bending of light, whereas reflection is the bouncing of light when it strikes something. Refraction, we can see that through this glass bubble here, that light is distorted because it's going through it and bending. Now let's talk about sound. Sound does, remember, require a medium to travel through. And this is why the speed of sound can depend on how bouncy the material is going through. It's how dense it is. This is why sound travels better in solids and liquids does in gas. There's just more vibrations to bounce. And because sound is vibrations, it's like we're hearing vibrations. That's what we are. We make vibrations with our vocal cords when we're speaking. And that loudness is measured in decibels, and that frequency is pitch. And sometimes we do see sound waves depicted as a transverse wave, but in reality, they're a compression wave. Right? They're a longitudinal wave. And we can kind of see that depicted here in this image. Now, one of the interesting things about sound is the Doppler effect. And this is the apparent change in frequency of a wave from a source as perceived by the viewer. So our perspective. And as a wave-producing object moves away from observer, it'll get lower because the frequencies are further apart. But as it comes towards us, it's going to be a higher frequency because the wavelengths are closer together. Here's a picture illustrating that, the direction of the person heading towards one observer on the right. Those wavelengths are closer together, so we get a higher frequency, and lower because it's on the other side, they're further apart. Let's look at some examples of this. Here's a classic example of a fire truck. And this is not about volume. This is not about how loud, right? But this is about the sound, the frequency, the pitch. You can hear it become higher and higher frequency, and then once it passes, we hear the lower frequency. It gets louder and louder until it passes us, and then a higher and higher frequency as well. And then it becomes lower. Here is another example. And you can imitate this yourself, but just pressing on a car horn and driving by, you have definitely heard this before in your life. I'm almost positive. Is this something you've experienced? I often hear it with when the ice cream person comes around in their van playing that music. There you have it, the Doppler effect. The Doppler effect. Now, thanks for watching, and hope you learned something about light and sound, and be well. Later.